All right, time travel today. Do you ever wonder what it's like to go in the future or go into the past? A lot of science fiction on this. A lot of people speculating. It's a good plot device to learn about society and yourself. And now we'll find out a little bit of the concepts of what physics has to say about the concepts. So this is the next lecture we'll deal with that. I am Robert Nemroff. This is Michigan Technological University in the beautiful Upper Peninsula of Michigan. And here's the obligatory second slide that says where you are and what's going on. So you stumbled upon this on iTunes or something, or the web. And so this is Extraordinary Concepts in Physics is the official name. Physics X is the unofficial name. And you can find us here. And if you can ever read this on the slides, which are available on the web, then you'll know where to go on the web to find us, paradoxically. Okay, so time travel to the future. So there's two kinds of time travel. One is time travel to the past. One is time travel to the future. So we'll do the less controversial one now. Can you go to the future? And the answer is yes. And in fact, the Planet of the Apes series was about that. And that's the movies. There's Joe Haldeman book, the Forever War, really cool. About travel to the future. So there's nothing really wrong with this. This is just the twin paradox. The twin paradox could be just going really fast and coming back, or going near a black hole for a while and then coming back. And if you and your identical twin, you'd come back and you'd find that your identical twin, assuming you're the one that went out, would be much older. So you've traveled to the future. So if you could construct a technological ship like this, you could go away and you could find what happened to your children and your children's children and that stock you invested in, how that's doing. You can travel to the future. The problem is that it's expensive and it's hard to do. We yet, besides going just a small fraction of a second into the future in airplanes and spaceships circling the Earth, we really can't go any significant. We can't hit the speeds. We don't have any local black holes we can go to. So it works in theory. It even works in practice to very small amounts. But sadly, we're stuck in our own time. Travel to the past. Now we hit a hotbed of controversy. First of all, contrary to science fiction movies, it's never been done. It is controversial. There are, including general relativity, you can come up with ways of doing it. However, people keep trying to undo it. So it's a little bit like the spam wars, where you get more sophisticated spam and more sophisticated spam protectors. You get more sophisticated ways of trying to get to the past that seem to be physically okay, but then other people analyze it and say, no, that really doesn't work. You can't really do that. So generally, papers about travel to the past are not thought to be part of mainstream physics. It's thought to be a little bit outside the mainstream. So, for instance, were you to apply for a grant based on a way to make a time machine and travel back to find out what the Civil War was all about, they would reject your application because no one really believes that such a time machine can be made. We need to have a lot more smaller things. The physics has to be better defined. Small journeys to a fraction of a second in the past has to be done. So don't bother applying. The major agencies will reject your applications. There are many interesting paradoxes that come up, the most famous of which is the grandfather paradox, which I'll discuss at the end. What no one seems to mention in these many science fiction movies is that things don't seem to conserve mass, energy, momentum, or angular momentum when people pop out of time machines from the future into the past. However, as I mentioned, it's a very common plot device in science fiction because it tells us so much about ourselves. So the most famous paradox is in time travel to the past is the grandfather paradox. So a person travels back in time and kills his or her grandfather. This happens before they had children. So then the question, how can you exist then? If your parents don't exist, so you can't exist, so you can't go back and do this. Now, it doesn't have to be a grandfather. And yes, you could have killed your grandfather or whoever it is after they had children. So there are ways of getting around some of the details of this. But the crux of the matter is that could you go back and do something that would make it so that you can't exist right now? And so the grandfather paradox comes up with a clear way of doing this. So So another way to visualize this is, let's say you went back in time and you stopped yourself from entering the time machine. So you go to a lot of effort. You contrary to what I said before, you get a lot of money. You build a fancy time machine. There's a big ribbon cutting at the opening. You start walking toward the time machine with your special time hat, giving your wave to everybody. And suddenly, a copy of you appears before you and tackles you and nails you to the ground before you can get into the time machine. That's paradox. So how can this paradox be resolved? Well, there are several ways people have tried to investigate this. One is that maybe this multiverse, parallel universes thing is true so that you can only travel in time travel to a parallel universe. Therefore, history remains intact at the time of arrival, and anything goes after that. So you might be tackled by your twin. You might be able to kill your grandfather as a little child. But so what? Life just goes on. You're in a different future now. So another way is the restriction action resolution. So actions are restricted so you cannot kill your grandfather even if you try. So there are some science fiction based on this, and we'll get into this later on. The Novikov self-consistency principle essentially says this. Or there's the destruction resolution. Killing your grandfather will cause the destruction of the universe. So it should be avoided at all costs. People, if it becomes accepted physics that that's going to happen, there will be lots of people trying to stop you. At your ribbon cutting, the army troops will show up and shut down your time machine because they don't want the universe to end. Predestination resolution. Whatever time travel does is really supposed to happen, even if the time traveler didn't know it at the time. So this happens a lot, particularly in Star Trek, I noticed. So Star Trek people, they go back and then in the closing scenes, they find out this was always supposed to happen. One really cool thing about this that isn't considered a lot, and that I think is somehow key to the matter, is just concentrating on information. As you know, things like faster than light depend on, can information travel faster than the speed of light, real communication information. So sometimes also it looks like the entropy and Maxwell's demon might depend on information. So let's follow the information. It's like follow the money. Let's not worry about traveling and killing your grandfather. Let's talk about an idea. What happens if a time traveler shows up and gives you an idea? If an idea comes from a time traveler from the future, where did the origin of that idea come from? Yeah, it's a problem. So new information has to have an origin. It can't just generate itself, it seems. So in order to keep information clear, ideas as to where information comes from, that gives you an ontological paradox. So the Hawking paradox says if time travelers exist, they would be here now. Since they are not here, time travelers, and possibly time travel itself does not exist. So this is sort of an experimental approach saying, well, Hawking has lots of thinking about whether time travel exists or not, but in this particular line of logic, he might throw up his hands and say, well, I don't know. But I'm going to do an experiment, and the experiment is, where are the time travelers? Time travelers come up to me now and tell me, listening for a sign, oh, didn't hear it. So why not? So then that experiment, there's no time travel. There's something called the Fermi paradox in the intelligent alien life search, which is similar to that, and we'll talk about that in other lectures. Carl Sagan, the famous science popularizer and the famous planetary scientist, said that perhaps they are somehow disguised. Physical laws might say they can't be seen. I remember an Isaac Asimov's story where you could go back and see the past, but they couldn't see you. So they're sort of like ghosts, but we can see ghosts or else we wouldn't think they exist. So these would be truly invisible ghosts that are around somehow. Can they affect things, I've been asked. I don't know. I would guess not. If they don't have any, if they can't be seen, if they can't be heard, they can't affect things. But you could go back and get information about the past in this. So they might not want to be found because they get a personal gain out of not being found, and maybe they want to avoid paradoxes in the future. Okay, so how would we find time tourists? So let's turn this around. Hawking says they're not here. Well, maybe they're just not going up to Hawking. Maybe they're not going up to you and me. Maybe we got to go find them. They're too busy doing stuff. They're too busy winning lotteries. Why do they want to come up to me when they could be investing in the lottery and taking that money, putting it in a bank account, and then taking it out back in their own time? What would they want to come to me for? I'm just boring to them. So maybe we got to go find them. We're just not interesting enough. Also, this has happened on the asterisk. People occasionally will post a photograph saying, this person looks like they're from a different time period. So there's photographs from like the 1930s, I think, and there's somebody who seems to have modern sunglasses and a modern coat is standing in a crowd, and they're circled. How can that be? Well, people dressed all kinds of ways, all different times. If you look at enough old photographs, you'll see some odd things. But how do you do the statistics on that? So it's one of these statistical arguments. How can that be? Maybe it can be. I don't know, but maybe they're not from the future. Here's one thing that I actually have been interested in. Every now and then I have a hobby of considering things like this because I find stuff like this fascinating. There are search engines that make their search terms public. Let's say people searched for stuff before it happened. Let's say a time traveler went back in time and they forgot what time it is. They didn't know that the great asteroid of 2015, that's actually a joke from Third Rock from the Sun, didn't hit us yet. So they say, like they search for the great asteroid collision of 2015, but they forget that it's 2010 when this lecture is being. Then this search term would turn up on a search engine, and it would be then after 2015 we'd say, wait a minute, this person searched for something they could not have known about. When a famous person dies unexpectedly, so sometimes some students of mine go searching through search engines and trying to find comets, for instance. Famous comets come around. We didn't know they were going to be bright. So comet, I don't know, I can't think of a name right now. Comet Linear, Linear the Fourth. Someone searching for that a year before it happened would be strange. So we haven't found any evidence of that. So preliminary searches hasn't found for unusual time tourists forgetting what time they're in. So Hawking then made the chronology protection conjecture, which said that the laws of physics will somehow prevent time travel, which we will see are closed time-like curves in general relativity in all but microscopic scales. This applies to normal matter, matter that satisfies the general relativity weak energy condition, which you can follow that link and find out what that is. It's a weak way of saying energy is conserved on short times and small scales, although energy is not generally conserved in general relativity. So it is generally thought that the chronology protection conjecture does not apply to matter with a negative energy density like dark energy. So that could be a loophole. So it is impossible, the Novikov self-consistency principle says that it is impossible to create time paradoxes. The probability of something occurring, if you could come up with a math that would create this, would show you the probability goes to zero. So changing the past paradoxes are guaranteed self-consistent in that they only create a closed loop of self-adjusted, cyclical, self-consistent way. So here's another closed loop. Using the Novikov self-consistency principle, you can test it assuming there was a time machine. So the time loop logic says that let's say we wanted to create a prime factor f for a very large number n. Now this is going to take years and years on computers because n is so large. So if I give you this for homework, it would take you years to do it. However, if you had a time machine, you could do it and then send the answer back in time. And here's the algorithm for doing that. And if they send the answer back in time, then you get the answer and then you say, oh, so this is actually a fast way of computing things. You get one of these time machines, you compute things, then you send the answer back in time and you've created a super fast computational device. Back to my pet peeve. One of my pet peeves, many times in movies, people go into time machines and then they come out and they see themselves. But wouldn't there be twice the mass then? Isn't mass even conserved on small time scales? It seems to be a gross violation of that. Also, the Earth goes around the sun, the Earth spins. If somehow they could find the time machine and come back out of it, wouldn't they be flying out at some fast speed relative to how fast the Earth was spinning when they went in? So there seems to be all these minuscule kind of practical paradoxical things that would have to be solved if you actually wanted to go into the past. And with that, we will leave you to time travel 2 in the next lecture. See you soon. Or in the past. Bye.